We're asking our walls to do a lot, especially here in interior Alaska. We can have 30 below temperatures outside, 65 degrees above inside, so we've got a 100-degree temperature swing in between the siding and the sheetrock. What we're curious is what's going on inside that wall system. And when you think about it, the exterior walls on a house are probably the largest surface area exposed to the elements. And what that means is that if your wall system isn't performing as it should, you could have up to 30% of your total energy losses in your house going out your walls. And so today, when looking at walls, we're going to try to keep three concepts in mind. We're looking at heat losses through conduction. It's also called thermal bridging. We're looking at how moisture travels through a wall, and we're going to look at how a wall deals with air leakage. And we're going to look at new walls, and we're going to look at some retrofit walls. But everything we look at has to deal successfully with those three issues. So climb on board. Our journey into cold climate wall construction is starting here at the CCHRC Research and Testing Facility. And what we're looking at here is a drywall surface, just like any other you would see in a home. But what we've done is we've taken a 3-foot exterior door, pulled it out, and in its place we've built a frame wall. This is a frame wall that would represent the typical construction methods and techniques used to build homes, residential homes in the Fairbanks area, probably anywhere from the 1960s to the 1980s. And keep in mind, this was a time period before we had some of the techniques and the knowledge we have today to build tight super insulated structures, but also before some of the materials that we take for granted today were even available. And some examples here would be Tremco acoustical sealant. This is great for sealing vapor retarders. We've got spray foam for insulating and sealing gaps. We've got red tape for also sealing different places, and we've got vapor and airtight electrical boxes. And these are just a few products that have come out in recent years that make wall systems perform a lot better. And there's three things we're primarily interested in. We're interested in air leakage, just to see where the leakage points are in this wall. We're curious about moisture movement through this wall. So we've got, hot, humid air. There's water vapor in that air. How is that traveling through this wall, or isn't it traveling through the wall? And we're also very curious about heat losses, and specifically conductive heat losses. There are different materials in this wall, and different parts of this wall will lose heat at different rates. We can't tell on the outside, but we've got a bag of tricks at our disposal that'll help us do some diagnostic work long before we even get into the wall. So what the blower door is doing is simulating a 20-mile-an-hour wind, and it's pulling that air in through any leaks in this wall, and the obvious two leaks are the outlets. In both cases, I can put this smoke puffer in front of the outlet. No smoke is going anywhere near the two holes. My hand can tell there's air leaking through that. The other thing this blower door test does is by bringing in this cold air, it's creating extra cold spots in that wall, so when we grab that infrared camera next, some of these areas will be extremely cold, so it'll help us highlight those cold spots so we can point them out. So looking at this infrared image in the upper half of the wall, we can see that the outlet is dark blue. And that's no surprise because we were pulling in the cold air through that region. But we can clearly see the wood framing going down the center. We can see the sheetrock screws outlined. They're highly conductive, so they're conducting heat through the outside. But then we've got a really interesting anomaly up here at the top of the wall in the upper left corner where there's a very dark blue patch. So there's some pretty extreme heat loss going on in that area, so that'll be worth exploring. So now that we've done some diagnostic work on this wall, we're actually going to see what's going on inside here. We know that there's some anomalies. We've got some cold spots, and we've got some air leakage around these outlets. And we can see here, nothing is sealed here. There's a large gap around this side. I can look inside there, see where the wires are coming out. That wasn't sealed either. That's really typical for an older home. One way to fix this is to pull this outlet out and then get inside here and seal between the electrical box and the sheetrock, and as well seal inside there where the wire comes through the wire clamp and any other holes. But make darn sure the power's off. If you have any questions when you're messing with electrical systems, talk to an electrician. Time to see what's behind the curtain. First thing we come to is the plastic vapor retarder. And what this is it's your primary pressure boundary that separates the indoors from the outdoors. It's designed to stop air leakage through the wall system, and it's designed to stop moisture flow through the wall system. And it doesn't matter if the air is leaking into the house or out of the house, either way it's costing you money. Now it takes two things to produce air leakage. It takes a hole and it takes a pressure difference between inside and outside. And that's where in an extreme cold climate like Fairbanks, we get tremendous pressure differences from one side of the wall to the other because of the extreme cold. So at any given day during the winter, you have no idea really how much air is going in and how much air is going out. Not a lot of care was given to cutting an outlet and sealing this area around the edges. It was stapled rather loosely, but every place you've got a little hole, it starts to add up. And you really don't know how much is going in and how much is going out, but you do know that it's leaking more the colder it gets. I would say for a typical house, an older home, you could be leaking, well, in a bad case, as much as half of your air in the entire home in an hour. So it really, really makes a difference to have this envelope be tight, have a tight pressure boundary. We generate a lot of water vapor just from living indoors. Cooking, eating, breathing, showering, all of these activities produce water vapor. And there's a statistic that says about 98% of all water vapor movement through a wall is due to air leakage, that those two are very, very related. So any places we have holes and penetrations in this wall system, such as we examined earlier, if there's a moisture problem, those could also be potential entry points for water vapor. There is a thin layer of frost. You can see some insulation is stuck to that on the sheathing. So we've got indications that we've had fairly high levels of humidity in here and some air leakage. And so what's happening is that air is traveling through this fiberglass until it hits this sheathing where it cools, and then that water vapor condenses out and becomes frost. Generally speaking, what happens in the spring is that these walls dry out fairly quickly, so the moisture is not in there long enough to cause a problem. Is this desirable? You've got moisture in your wall system? I'd say not. But in these older homes, these systems work because they dry out fairly quickly. I would say a much better alternative is a modern wall where we're controlling indoor humidity levels with mechanical ventilation. We've got adequate amounts of insulation, and we've got a very, very tight wall that minimizes the moisture and air exchanges from inside to outside. Some of the issues that came up on the thermal imaging on the infrared photos are starting to make more sense here. We can see the insulation wasn't quite put tightly up here to the top plate, so we've got a gap here. Well, it's very cold outside today, 30 below. Inside it's about 70 degrees, so we've got a tremendous potential for heat loss just in this one spot. Also looking at these outlets, this upper outlet is probably about 2.5 inches deep. That insulation's compressed back there, so it's not performing anywhere close to its rated R value because it's only about 3 inches thick. Down here on this bottom outlet, the insulation was cut around to fit the box, but there's little air gaps everywhere, and that's what we saw in the imaging camera as the outlet was kind of a dark blue. We can also see back here there's a wire. So in order for this insulation to perform well, it's got to be carefully cut and fitted around this electrical box, and this is always a tricky area. And on these older homes, a lot of times, not a whole lot of care was given to this kind of installation, and so you could have things add up in this wall that would add to some more heat losses. So now what we're going to examine is the source of that dark blue line that we saw in the infrared image. And what that is it's this wood stud right here. And what's going on is this wood stud is far less insulative than the insulation here in the middle of the wall. I would say a wood stud like this, 2x6 stud, probably has an R value of about 6 or 7. When you compare that to the fiberglass, which is about R21. Well, when you factor all the wood that's in a wall system, you've got somewhere between 11 and 25% solid wood. That will greatly bring down the wall R value. In this photo, what we're looking at are some classic telltale signs of conductive heat losses through thermal bridging. And there are various darker spots on the drywall. What's happening here is over time, the colder spots in that wall are attracting condensation. And as part of that process, the microscopic dirt particles that are in the air are getting deposited on that drywall as well. Over the years, these spots become darker and darker, and they clearly highlight places like where you have studs, where you have fasteners in the drywall, or just simply places where insulation is missing. So today we've looked at an example of a typical wall in an older home, and we've taken off the sheetrock and we've looked at layer by layer how this wall is actually doing from an energy perspective. And for any wall built in a cold climate, it's got to do three things. It's got to address moisture travel through the wall, it's got to address air leakage, and it's got to address thermal bridging, where you've got heat losses through the wall which conduct through the studs or other areas. And in that perspective, these old walls, they did just fine. But I'd probably make an analogy to a down coat, where someone gives me a nice new down coat and then says, well, I'm going to poke a few holes in it here and there and maybe take out some of the insulation here and there and put in some slightly worse insulation, and then here's your coat. So I think this wall system did well in its time and at a given fuel price, but as we're seeing fuel prices going up, it may make more sense to invest in a better wall system or make improvements to an older wall system like this. You're probably wondering, I have an older home like this, what do I do about my wall system? How do I make it better? So in the next part of the video, we're going to take a look at two different approaches of outside insulation that can address an existing home with an insulation retrofit and upgrade the performance on your home and bring that up to what we would call a modern standard. And then later we're going to look at those same two wall systems and how they would work for new construction. This is actually a classic case. It's 2x4 wall construction. How old is the house, David?
1973.
Okay, well that's pretty typical to that era of house, and I would guess this whole subdivision is probably full of houses very similar to this one. It's 2x4 walls with 6 inches of foam. For us in interior Alaska, that's a great insulation ratio. You've got about 70% outside insulation, 30% inside insulation. Keep in mind that this is a 2x4 wall on the inside. It's framed 16 on center. It's got tons of wood. I doubt the fiberglass was put in real well, so I'm guessing that this wall is actually probably performing at an R8 or an R7 even. And so we've got a really good insulation ratio with a true probably R26 out here and a wall inside that's somewhere between, I'd say, R11 and R7. Your first floor rim joist is about at this level, correct then? So
I'm probably down 4 inches below the rim.
okay, so you're going to insulate the crawl space then on the inside and bring that up and carry the boundary, thermal boundary through that way.
Yep.
That's one of the issues you face with these older places is you've got sidewalks in the way, you've got staircases, so it's almost impossible in many cases to dig this out and insulate it all from the outside. But doing it from the inside works out just fine too if you've got, you know, the opportunity to do so. But certainly having the insect screen and the varmint screen to keep the critters out is nice.
There's very few penetrations. There's only 3 on this wall. I mean, on the 2 walls combined, there's only 3. There's just there's a little vent, a little range hood, a dryer vent, and then this window.
Well, all of them look like they're very well sealed. And that's the critical thing, is just to stop that air leakage through the wall. So, you know, you're stopping air leakage, so you're stopping moisture travel through the wall. So
Okay, good.
Nothing's moving through. This is a nice detail too, sealing around this. So this is your jamb extension. You'll have finished trim around that. In wet climates, sometimes they slope these down, so you've got drainage out. But this looks like a really tight wall. As long as none of these screws, you know, end up in the wall cavity, they all should hit a stud. So that screw point is bedded in wood rather than out in space in the wall where it'll attract condensation. Even little details like this are worthwhile because this wire goes all the way through to the inside of the house to the TV. So, you know, it's small, but you might have, you know, a dime-sized hole that goes all the way through. Well, the place to stop that air leakage is first off at that drain wrap, that house wrap product. You would tape basically around this wire to seal it. Then every layer of foam, you'd spray foam around that hole too. So you've got a belt and suspenders approach where you've got every step of the way, you've made an effort to stop air leakage through the wall. And it makes a difference. You know, you got one here and one there, and there's a bunch of other wires further down the wall. Those are all points where you could have some air leakage. You could have some moisture traveling through that wall with that air. So cut that down. Well, you've got 2 sides insulated.
2 sides,
so
yeah.
I don't know if you'll be able to tell if it's any less drafty, but
No, that yes, we're getting a radiative savings, but our house is still really drafty.
Yeah, you're stopping, conductive losses through the wood studs with the foam, and you're stopping the air leakage, with the foam once again too. So it should be, at least from a fuel bill standard, you should see it on there. But if you've got air leakage through the other parts of the wall that haven't been worked on yet, it may not make a difference in how it feels. That's hard to say. It'll make a tremendous difference when the whole thing's cased in.
Yeah.
This house is now very thermally efficient. It's got 2 overlapping layers of foam board, and so it's very airtight. You're eliminating air leakage through the wall system. You're cutting down dramatically on your thermal bridging through the wood framing. Also, this house manages moisture very, very well because the original wall stays warm enough that it never attracts condensation now that you've got 6 inches of insulation on the exterior. In this case, the house will receive vertical siding, so the furring strips have been applied horizontally. And the furring strips here will carry not only the siding, but they're also the primary attachment point for the foam board. When all the walls on this home are completed, it will become very, very energy efficient and be comparable to that of a new home. This photo shows an existing home undergoing a double wall insulation retrofit. What we're looking at here is a new stud wall that's held away from the original home, and that will separate the old wall from the new wall and eliminate heat losses through thermal bridging. A layer of Tyvek house wrap will be applied over the exterior of this structure, and then a dense packed cellulose will be applied into each one of the new stud bays. A blown-in insulation product is a good choice for this kind of a situation because the blown-in insulation will fill in around all the irregularities created by the existing siding. This house will be then very thermally efficient. Air leakage to the dense packed cellulose will be minimal. Here is a photo of a wall system in new construction that uses an outside insulation approach and is dubbed the remote wall. Both the vapor retarder and the wall insulation are attached to the outside of the structure over the plywood sheathing. The multiple overlapping layers of foam board encase the building in a continuous layer of insulation, which both effectively minimizes thermal bridging and also makes the structure extremely airtight. Added benefit to the remote wall system is that the foam board insulation is moisture resistant and therefore can extend below grade to insulate basement walls and crawlspace walls. Areas around the windows and doors that typically use a lot of wood are now well insulated on the exterior to minimize heat losses through the wood framing. Since this system is airtight and places its insulation on the outside of the walls rather than the inside, those walls stay warm and are much lower risk for attracting condensation. In this photo, we are looking at new construction using double walls. In this particular case, the vapor retarder is placed on the exterior side of the inner wall and serves as the primary barrier which stops air leakage and moisture migration from inside the house into the wall system. Since the two walls aren't touching other than at doors and windows, heat cannot conduct through the wood framing. This eliminates the bridging losses in this area. Once the exterior wall is completely covered in house wrap, then cellulose insulation can be blown in from the top of the wall. The blown-in cellulose is installed in enough density that it also doubles as an air barrier, creating a very tight and energy-efficient wall system. Where we stand today is a building philosophy that says build tight, ventilate right. And what we are trying to do is create an indoor environment that is as separate and as controlled as it can be in relation to the outdoor environment. So we're trying to minimize our heat losses, we're trying to minimize our air leakage, and we're managing indoor humidity levels with mechanical ventilation. And the idea is the more we can control and manage our indoor living environment, the longer our home will last and the healthier our occupants inside will be.